All right, so I haven't had a lot of time to look at the exams. I've looked a little bit, kind of the multiple choice, what the scores look like. I don't know if there will be a curve. It kind of depends on what that average ends up being. If there is, I'll put an announcement on Canvas and let you know what that is. Also, once they're all graded, kind of like the last exam, it looks like right now it's out of 104. So I'll post another one where it's only out of 100, and that will kind of give you the idea of what, the exact percent you got on it once I have all those short answers graded. I'm hoping to have that done before we meet on Tuesday. My guess is it'll be close. I've got a couple other sections as well, so I'm trying to get through all those by the beginning of next week. But I think that'll happen. Once I have those all graded, and I'll talk more and show you on Tuesday on Canvas, I'll identify your lowest and your kind of highest exam and then weight them accordingly. So it'll give you a little bit better idea of kind of where you're at in the class right now. But until I get that, all the second exams graded, I can't do that. So that should be coming on Tuesday. Other than that, just before we kind of get started, I'll post an online quiz today that goes over whatever we talked about today kind of fits in with that. It should be pretty easy. It's really actually going to look like a survey because I'm just kind of asking you some things that are difficult for you and trying to get an idea better about how to approach this next topic, which we'll start today, which is population, hypothesis testing, and confidence intervals. So we're going to use a lot of what we did before, throw in a couple of new things, but it shouldn't be anything wildly new. I'll also put a Learn Smart up. That'll be Tuesday before we start class. It'll be kind of over population. So we'll cover some of it today, but the Learn Smart will go a little more in depth to kind of prepare us for next week. Let me make sure. Other than that, are there any questions for me before you go?
The Learn Smart will be due next Tuesday.
Tuesday, yep, before we start class. Yep. And I'll probably post an announcement after class today that kind of, mentioning the online quiz, the Learn Smart, and then, those two things. All right. Actually, we'll see where we get to at the end of the class today. I might have something else to say, but for now, I think we should be. Is there additional hypothesis testing? No, so that assignment, and let me make sure, because they had the same question as the person that's here today. So I believe, all right. So I posted an announcement when I posted that because I want to make sure that it was clear, like this is not an assignment. It was just practice if you wanted some problems going into that exam. If you're still not feeling comfortable with hypothesis testing, you could still kind of work on it. There's no extra credit. It's worth 0 points. I know it appears like it was worth points on there, but that's just because the Connect platform is kind of showing you what it would be if it was an assignment, but I've got it set just as kind of a practice. So our next Connect, I'll probably assign, depends on how far we get today. I might put it up there today, just so if you want to start working on it, you can. Won't be able to do a whole lot, but kind of as we move through material next week, you can kind of work on that more and more. So I probably will get that posted after class today, but the due date's going to be quite a ways off because we still have a lot of material to cover until you could answer every question there. Okay. Any other questions? Okay. All right. So today, I've got the lecture slides posted. It looks like it's week 13 because, we kind of skipped week 12 and we're doing some exam review and kind of finishing up hypothesis testing. So we'll call this week 13. And then I also, in the in-class data folder, we'll kind of be working with this population HT blank. So population hypothesis testing, we'll kind of work through that. And once we get there, I think I'll have a little bit more to say about that. Okay. So before we had examples, we only had one population we were sampling from, right? We had a sample mean, we had a sample proportion. So what we're now going to do is build confidence intervals and do hypothesis testing for the same three scenarios, right? One where we have the mean and a known population variance, proportion, one where we have a mean and only sample variances, right? Same kind of thing we did before. It's just now we're going to be comparing the difference in the means of two populations, okay? So once we work through all that, we will have an example, we will have something that looks a little bit new from what we were doing before, which is this idea of matched pairs. But we still have a ways to go to we get there. I'm just kind of setting us up. Here's what we're going to have to be covering kind of over the next, probably about a week and a half, 2 weeks. So the motivating examples would be something like this. And I'll go through these quick because we're going to actually solve these once we talk about what is different from what we're doing in one population. But maybe I have, 40 econ majors and 50 theater majors, and I want to know, is there a difference between their starting salaries? So I take a sample of econ majors and of theater majors. I find the sample mean. There's a known population variance. Can I build a confidence interval for what that true difference is? Is it positive? Is it negative? Right? Are they any different? We could also do a similar thing with proportions. So maybe I've got 2010 and 2011. I had a survey asking about the views of the Affordable Health Care Act. And then I want to say, okay, I've got 0.48 in 2010, 0.51 in 2011. What's the confidence interval for the difference or the change in kind of the views of this Affordable Health Care Act between these 2 years? Or I might have texters, non-texters. I have their average response times, but I only have this sample average or a sample mean. So can I build a 90% confidence for what's the true difference in response time for drivers who are texting versus those who are not? Okay, so that's kind of the general setup, right? We're going to have 2 populations. So we can start out thinking about the econ theater majors. Maybe population 1 is my econ majors. I know that there is some true mean for that group. We'll call that mu1, right? Kind of using subscripts to identify this is our population 1, our econ majors. Maybe I can't see this, but I know it exists. I also know that the population variance exists for that group, whether or not I can see it. I can then take a sample from that population. I'll see a sample mean, and then I can, however many observations I have, I'll have a sample size that I took from that group as well. I then can do the exact same thing for a second population. So maybe my theater majors. I know they have some true population mean, some true population variance. I sampled 50 theater majors. I then calculated a sample mean and had that sample size of my theater majors of 50. Okay. So before I go to the next thing on this slide, I want to try to give you a little bit of intuition. I'll lay some things out, but I'll try to give a nice visual as well. There we go. All right. So what we know is going to be true about the distribution of sample means. Let's say for group 1. So maybe this was our econ majors. So we'll call this group 1. I then have group 2, right? I know the distribution of my sample means should be normally distributed around whatever that true population mean is. And I could actually even go a step further where I know that and it's kind of hard to denote this, we'll call this, the variance of the sample means from group 1 will just be the population variance of the data we sampled from divided by the sample size. But now we're just saying this is from group 1. We also know that for group 2, their sample means will be normally distributed around whatever the true population mean is for group 2. And then the variance of our sample means for group 2 will be the original variance of the data we sampled from over our sample size. So here we're just plotting these 2 distributions of sample means, right? One for group 1 and one for group 2 kind of next to each other. So if this is the scenario that we have, what we then can think about is, well, what if the statistic I'm interested in is the difference in these sample means, right? I'm no longer just concerned about one, I'm concerned about both of them, and I'm looking for the difference between them. So how would that difference be distributed? So we could look at kind of the mathematical proof and work through it. A lot of it, given the prereqs of this course, it may be pretty more confusing than helpful. But the main result, if we work through some of the math theory here, would be that if we're looking for the difference in our sample means, and it kind of makes sense, it should be normally distributed. This distribution of the difference in sample means should be normally distributed. And think about what's the most likely difference I see? Well, the most likely sample mean values I see for group 2 would be here. The most likely sample mean values I see for group 1 would be around here. So the most likely difference I would see would be just the difference between those 2 population means. Right? Now, what are the next most likely outcomes I could see? Well, here and here, and then here and here. So now this difference and this difference and this difference, these are going to be the next most likely differences I see, but they're a little bit less likely. Right? And as I start to think about, well, it's very unlikely I see a sample mean way out here and a sample mean way out here. So then when I start to think about really large differences, they're very, very unlikely for me to see. So what ends up being true is that when we're looking at the difference in our sample means, it should be centered around whatever that true difference is between the population means. And then any difference kind of in either direction there should be less and less likely. Any questions over anything I kind of have up here so far? Okay with this? All right. So what do I say next? Okay. So another thing that we might want is what's the variance for the difference in my sample means? But once again, there's a mathematical proof to support this, and as we kind of work through, maybe I'll show you some data like I have before where we can prove this to ourselves in data. We don't have to worry about the math theory, but it kind of is intuitive. If I want the variance of the difference in my sample means, it's simply the variance, well, here, I can think about it this way. It's the variance of each sample mean, which I have those up here. So another way we could think about this is, it's the variance from group 1 divided by the sample size from group 1. Oops, sorry. And then it's the variance of group 2 divided by sample size for group 2. I'm just plugging those equations I had up here, right? I know how to calculate the variance of a sample mean, and the variance of the difference in the sample means will just be, we'll add the variance of each one together. And then if I want the standard deviation, the only other step I would have to do, so let's say I want the standard deviation of the difference in my sample means, I would just have to take the square root. Well, now I've got a normal distribution for the statistic I'm interested in. I know its mean. Its mean will be the kind of true difference here. So we can think about this as the mean of the difference in my sample means. And then I have the standard deviation. Well, if I have the mean and the standard deviation, I can convert this normal distribution into a standard normal distribution. And it's similar to what we were doing before. Okay? So that's kind of what's on the rest of that slide when we go back here, but I'll leave this up on the screen for a second. Actually, I think we'll keep doing some work here. So if I've got this as my distribution, right? Let me make sure you guys can still see some of this. Okay. Then we can also do confidence intervals here, right? Because I have known population variances. If I want to calculate z-scores, I know they'll come from a standard normal distribution. So what were we doing with one population? When we wanted to build a confidence interval, we looked up the z-score, or the number of standard deviations away we wanted to go to the left and the right, right? That would give us kind of line up with our confidence interval. So whatever alpha we have alpha total outside the interval, or alpha over 2 on each side. We then multiplied that by the standard deviation of that sample mean. So we took our confidence interval, we built it around the sample statistic that we're interested in. We want to know where the population mean is, so we base it off the sample mean. We then use that standard normal distribution to figure out how many standard deviations to the right and left do I go. And if I want to go 2 standard deviations, then I need to multiply 2 by whatever the standard deviation is. And it's the standard deviation of the statistic I'm interested in. So here it's the standard deviation of my sample means, which I knew was equal to this. Okay. So with 2 populations, the statistic that we're now interested in is going to be the difference in our sample means. Because we have population variances, we can still use that standard normal distribution to figure out how many standard deviations away we want to go to the left and right. It's just that now I need to multiply that by the standard deviation for the difference in sample means, which we set up here was this equation. So I plug everything in. It's going to look a little bit more complicated, but it's really the same format we were using before. It's just that when I want to find the difference in sample means, right? I know the standard deviation for that difference will include both the kind of the variance from each group. Okay? So notice it's still build your confidence interval around the statistic you're interested in, Here we've got known population variances, so we can use the standard normal, and then multiply by the standard deviation of whatever statistic you're interested in. Okay? So it looks a little bit more complicated. There's a few more moving parts, but it really is kind of the same sort of setup here. Okay? Any questions on that before we keep moving? Okay. Good. All right, and I'll pop this up here in the bottom. So we kind of already said the mean of for the difference in our sample means is whatever that true population difference is, the true difference in the population means might be a better way to say it. And then our standard deviation was just add up the variance of each sample mean, and then we want the standard deviation, so take the square root. So we also kind of built out our confidence interval equation. I kind of lined that up to what we've done before to maybe make it a little bit more clear, or kind of give some context for this. But once we know it's the same kind of same procedure, we've got this as our confidence interval. So, and that's kind of like I was saying, like this is like what we had before was just the sample mean, and now our variance is a little bit different as well. So what are the steps going to be? They look exactly the same as what we were doing before with one population. It's just that now we have double of everything, right? Now we've got two sample means because we want to find the difference in them. So we need two population variances and two sample sizes. We're going to be usually given alpha. Sorry, yeah, you guys gotta let me know when I forget. I forget to do that almost all the time. So, or at least the very first time I switch over, it always does that and I forget. So, right, the steps are going to be the same. We've just got two sample means because we have to find the difference. We've got two population variances and two sample sizes we need. But once we have alpha, right, we look up that z-score the same way we were for one population examples, right? It's just what z-score gives me alpha over 2 in each tail. Once I have that, I really can plug everything into this equation. Now, kind of similar to before, I can do the intermediate step. Like I can calculate this standard deviation first and then just plug that in right here. And I think that is a lot more helpful in these two population examples because it just creates a lot less moving parts in your final equation you have to put in your calculator, right? If I have to enter this whole thing in where all these become numbers, it gets a little bit, I don't know, hard to look at and easier to make a mistake. So as we work through some examples today, I'll kind of show you what it looks like if we calculate the intermediate value, kind of adding an additional step here. Okay. So let's go back to that example we had. And I'll try to leave this on the same line. Where we had 40, so let's do, got my econ majors, I had 40 of them. Just writing things down so when I switch to the dot cam, I'll have all my information. My theater majors, I had 50 of them. The sample mean salary for econ majors was what, 45,000? Sample mean starting salary for theater majors was 33. And then we're given the population variance. This might not seem very realistic. It's usually not, but we have to start somewhere, kind of like we did for the one population examples. Eventually we'll get to a point where we can say, well, what happens if we aren't given this population variance and we only have a sample variance, okay? All right, so just written down everything that I wanted. If I want the 95% confidence interval, what would my alpha be here? Point what?
You said 90%?
Oh, sorry, I might have said 90. 95% confidence interval here, right? So for 95%, alpha would be, yeah, 0.05, yeah, 5% or 0.05. So write this over here. Okay. Now I've got everything that we need. Okay. Make this a little bit larger so it's easier to see, right? This is just everything that I was given. Well, if I know this is my confidence interval equation, I know that I'm going to need to look up that z-score, right? And I need the z-score for what? Alpha divided by 2, so 0.05 divided by 2, or the z-score that gives me 0.025 in each tail. Right? So if I want 0.025 in my tail, I'm going to go to, oh, I thought I had them pulled up. Maybe PDF crashed. Let's do this again. There we go. So we've got this standard normal table we know we can be using because we have population variances. I want 0.025 in the tail, so I try to find that value right here, 0.025, corresponds to a z-score of negative 1.96. So negative 1.96 would give me that area of 0.025 in the tail. Now, when it comes to confidence intervals, just like with one population, I don't want to use negative 1.96 because that's kind of already built into my equations, right? The negative 1.96 gives me the lower bound, positive gives me the upper bound. So really that z-score I want to use is just the absolute value, or 1.96. Any questions on that at this point? So when we look up that z-score, it's literally exactly what we were doing before with confidence intervals. Nothing's changed at that step. Now it has kind of changed. We have a few more moving parts here. So I'm going to go ahead and I'm going to calculate this intermediate value, which is the standard deviation for the difference in my sample means. I'm just going to calculate this guy. Okay. So I'll take the variance of the first group, which was what, 9,000, over that sample size, variance of the second group over their sample size. And what did I forget to do? Yep, I need the standard deviation, so I'm taking the square root of that. I can't remember. Oh, hopefully I have my calculator here. I forgot it because I took it out to use in my office. So I think it's 15 point something. If you want to help me out, otherwise I can switch to Excel here. I'm going to take a guess. 15.5. 6.7. Or maybe I'm thinking about this. This might be 50 something. Might be getting.
18.57.
There it is. 18.57. I knew there was a 5.7 in there. Okay. 18.57. So now that I have the intermediate value, it makes it a lot easier because I can just plug this in right here. Right? So now I've got everything I need. I've got 45,000 minus 33,000. Those are the two sample mean values I found. I'll then add to get my upper bound, subtract to get my lower bound, use that z-score I looked up, and then plug in that standard deviation because I calculated the intermediate step. Okay. So what should my confidence interval be centered around? Well, if I think about what was the sample difference that I found here? 12,000. So my confidence interval should be centered around that $12,000. I'll go a certain amount to the left and the right. If I do that, this is where I have this in the slides, if I can get back there. There we go. All right, so we identified everything we needed. We looked up that z-score. Now it's a matter of plugging everything in. So on the slides, I didn't calculate the intermediate step. You could plug those numbers in and do this all at one time, right? It's a little bit more complicated. It's up to you, whatever you feel, more comfortable with. But once we do those calculations, we would then have our lower and upper bound. Okay? So I'll talk a little bit more about the interpretation of this confidence interval on the next example. But the idea here would be with 95% confidence, I can say the true difference between econ and theater starting salaries is somewhere in this range. So, econ majors here with 95% confidence are making $11,964 or somewhere up to $12,036 more, okay? But remember, this is the range for the difference in those two. Okay? I think the next example will make a little bit more sense. This is kind of a narrow range, so it's hard to think about. But let's try to go through another example here. So maybe I've got, two states here, Indiana and Ohio, and I've got 24 years of data from each state. So this is going to be kind of a unique one in which, if I think about Indiana and Ohio being my two populations, but I've got 24 years of data for each one, so my sample size for each state is 24. Okay. I then was told, okay, in Indiana, over that 24-year time period, I found that, this is robbery rates? Yeah, robbery rates were on average 109. And during that same time period, those same 24 years in Ohio, it was 163. Okay. I was then given my population variances of 175 for Indiana and 497 for Ohio. If I want the 95% confidence interval, my alpha would be, it's the same thing we had before. So actually here, I could divide alpha by 2, then look that up in the table. But because we already looked at the last problem, I know that that's going to be what? the z-score that gives me 0.025, where did I have that? Here we go. It's always going to be the same, right? It's going to be the same value I found before. You have a question?
Mm-hmm.
Yeah.
So does it matter that they gave us that it was out of 100,000 people?
No, it's just a slightly different statistic, right? So the actual robbery rate is 109 divided by 100,000. That's just a really small value. So if we just remember that the differences that we're finding are always kind of out of 100,000 people, right? It just makes it a little bit easier to interpret. Yeah, if you want to, for the sake of understanding what we're going, you could even drop this. If you just think there's 163 crimes per year, right? And 109 crimes per year. If you want to think about that way, that's fine. Okay, so now we've got really everything that we need to kind of build this confidence interval, right? So it said, what was the true population difference between Indiana and Ohio? So, and I'm going to kind of keep switching here, so this might be, if you have any questions, make sure you stop me. So we're going to be using this equation right here, right? I'm going to be building my confidence interval for the sample difference that I found. Well, the sample difference I found is 109 minus 163. So I know that my confidence interval will be centered around negative 54. From there, I'm going to add and subtract. We said we can use that same z-score as the previous problem because we're using the same alpha. We're building the same confidence level, right? These values that we use for one population, when we were looking at these z-scores to build confidence intervals, they're going to be the exact same thing for two populations. We're using the same distribution. We're looking at the same alpha values. Now, the second part, I would probably go ahead and calculate this intermediate value, this standard deviation of the difference in my sample means. So let's see if I can get this all in the same, there we go. So the intermediate value here would be, and actually instead of 1 and 2, Indiana and Ohio, the square root of the population variance for Indiana, so 175, divided by the sample size for my first group, which was Indiana, so divided by 24. And then add in the second group's population variance, 497. And I had the exact same sample size for Ohio, so I'll be dividing by 24 here. Okay? So now that I have that standard deviation, I can just plug that value in up here. If we do this, let's see. See, you're helping me out today. So I got 5.29, right? Now it's just a matter of getting that plugged into my calculator. Okay? Any questions up to this point? We'll look at what the actual values here are in a second. Okay, so if I remember that the sample difference I found was negative 54, D doesn't make any sense at all, right? This is negative 54 should be smack dab in the middle of my confidence interval. It's not even in this confidence interval. If I look at the other three, it looks like it's kind of right in the middle of all of them. So they're all viable options other than D. So we identified everything we needed. We looked up that z-score. We didn't technically look it up on this one because we had looked it up on the previous problem. And then it was just a matter of plugging everything in. So if instead of finding that intermediate value, which was here representing the standard deviation for the difference in my sample means, I could plug it all in at one time, right? Makes it a little bit harder, but if I can do this okay on my calculator, it's perfectly fine. And I get this range of what? About negative 64 to negative 43, okay? So negative 64 to negative, whoops, I didn't want to do that. Negative 64 to negative 43. So if I'm thinking about how to start interpreting these, negative 64 to negative, I think it was 43. What this is saying at the 95% confidence level is that the true difference between Indiana and Ohio's robbery rates is somewhere in here. It could be here, could be here, could be here. Well, all these values are negative. So with 95% confidence, I can say that Indiana has lower robbery rates than Ohio, at least over that given time period. So the true mean is somewhere in this range, okay? So when I find confidence intervals that only have the same, so all negative values or all positive, I can then start to say, okay, one of these groups with this level of confidence has a lower mean or has a higher mean, right? Because if this difference is negative, that would mean that Ohio has to be greater than Indiana. Now it's maybe not as interesting. So let's say instead I'd went through, calculated it, and I get, I don't know, -80 to 20. Doesn't make sense for what we found, but let's just assume that this is what it was. Well, now the true difference could be down here. This is a negative value. Could be up here, it could be a positive value. So a negative value would mean Indiana is lower. A positive value for the difference would mean Indiana would have to be higher. So I could also see 0. If the true difference in my population means is 0, that would mean that they are exactly the same. Right? So, I mean, once we have a confidence interval that overlaps 0, it's got potentially the true difference is positive, potentially the true difference is negative, potentially it's 0. I really can't say much, right? It's not, I don't want to say it's not interesting, it's just that it doesn't allow us to say anything interesting, right? Because we don't know if the true population mean, at that level of confidence, we don't know if the true difference in population means is positive, negative, or even if it's not 0. Okay? However, the real one that we found, a little bit more power, we can say a little more of that because we can say with 95% confidence, the true difference is only these negative values. Indiana has to be lower. In fact, we could even say with 95% confidence, it's at least 43 robberies lower, up to potentially 64 robberies lower than Ohio. Okay. Any questions on that before we keep moving? Okay. Where are we at on time? All right. So if we can do confidence intervals, we can also do hypothesis testings. So we'll work through an example or two here. If we have time, I might show you a little bit of how to do some of this stuff in Excel, at least introduce the idea. So let's say we want to do a hypothesis test, right? We've got this range of values, but we want to be able to say, can I reject these values or certain specific values? So maybe I want to do the difference between two population means, and I could even do this for proportions. Today we're just going to focus on means, but I could do this for proportions as well. We're going to call we're going to call what that population difference is between the two means capital D, right? So if I'm thinking about here that true difference in population means, we're going to think about this as this is the true population difference, okay? Which means that we can do hypothesis testing for assumed true difference values, right? So just like before, if I can assume that it's greater than or less than or not equal to a certain value, this difference, right? And usually we're going to use 0 here as we work through some of these examples. I think we'll see why. And I'll show you what it looks like if we don't use an assumed true difference of 0, but I won't expect it on any of the Connect, Excel, or the final exam. Okay? So it's going to look identical to what we were doing before. It's just instead of the mean and the assumed true mean, we now have the true difference and the assumed true difference. We have a greater than sign in the alternative hypothesis, so we still have a right tail test, a less than sign, we have a left tail test, and we still have this not equal to sign, which is a two-tailed test. So same 3 types of tests we can do. And really, once we plug the values in here, it doesn't look a whole lot different, right? Once I have the assumed true difference in here, it's going to be almost identical to what we were doing before with one population. There's kind of like one caveat, and we'll get there in a little bit, okay? So we've still got our right, our left, our two-tailed test. The steps, exactly the same. This is the same slide I showed you with one population examples. We determine the null and alternative, figure out what our alpha is, use alpha to find critical values, calculate our test statistic. Is the test statistic in the rejection region? Or we could do the p-value approach where we calculate the test statistic, find the p-value, and compare it to alpha. All the steps are exactly the same, okay? So when we're thinking about p-values, we could really use the same setup we were thinking about before. The p-value for a right-tailed test is the area to the right of your test statistic. P-value for a less than or left-tailed test, area to the left of your test statistic, not equal to test, find the area in that tail, and then multiply it by 2. Nothing's changed. The procedure, nothing has changed. Critical values, nothing has changed. For a left-tailed test, they're still negative. Right-tailed test, they're still positive. They're the values that give us alpha in the tail, so they're the exact same values we're using for a one-tailed test. Two-tailed test, the only difference there we said was we have to think about there's alpha over 2 in each tail because we now have two tails. So now we look up instead of alpha, alpha over 2 to get our critical values. And we have pairs, right? We have one on each side. It's exactly what we were doing before. Nothing's changed. What has changed is our test statistic. So how do we get this test statistic? Well, remember, what we were doing with one population, I think my marker's done, so let me switch it out here real quick. When we had our one population examples, and let's just do a sample mean one, we would take the sample mean, and this was to calculate our Z statistic or our test statistic. We took the sample mean we found, we subtracted the assumed true mean, and then we divided by the standard deviation of that statistic we were interested in, or the standard deviation of our sample mean, which we knew was the square root of the original variance over my sample size. So if I now want that Z statistic or a test statistic for when I'm looking at the difference in means for two groups, well, now my statistic that I'm going to be looking at is the difference in sample means, right? I can almost think about this. Remember we said, where was it? That the true population difference would be the difference in the population means. So if I look at the difference in my sample means, I can think of this as like the sample difference I found. Kind of like P hat with the sample portion of this D hat, this is the sample difference I found. I'll then subtract the assumed true value of that test statistic. So the assumed true difference. I said a lot of the times this is 0, so this kind of makes it a little bit easier if this is 0. I'll then divide by, now not just the standard deviation of my sample mean, but the standard deviation of my difference in sample means, which, we were using that for confidence intervals already. So somewhere back here, we know is equal to this guy right here. Okay? So then I just plug that in. It's the square root of each group's population variance over that group's sample size, and then add them together. Okay? So it's really, it's this test statistic is like the same setup. It's just that if we're doing a different statistic, right, then we're going to have a different assumed true statistic, and the standard deviation of that statistic might look a little bit different. Okay? Any questions on that before we keep moving? So this is really the only difference. That once we have this test statistic, we use that test statistic to find the p-value, we reject if the p-value is less than alpha. All the steps are exactly the same. So let's kind of work through an example here. Now, I say everything's the same. Identifying the null alternative does become a little bit more tricky when we're dealing with two-tailed tests, and we'll see why in this example. So let's say I've got two time periods. So I've got a newer time period where I find the average number of tropical storms per year is 15.5, and an older time period, slightly more years, so my sample size will be a little higher for this group. And in this time period, I find a sample mean of the number of tropical storms per year of 9.7. So I want to determine whether or not tropical storms have increased during recent years. So what I'm thinking about here is, what's my alternative hypothesis? What do I want to test for? Well, it's a little bit trickier, right? So if I want to know whether or not tropical storms have increased, right, when I take the new time period minus the old time period, right, group 1 minus group 2, if they've increased, what would those values be for the difference? Remember, yeah, positive. So if I can think about that, that's okay. What I'm really saying is this difference greater than 0, right? That's what it would mean for, are they positive? Now, another way I could think about this is, I could say, okay, what do I want to test for? Well, I want to test for whether or not the newer average is greater than, what was the old time period? Ended in 1989, right? If they've increased, what I'm really thinking about is the new mean in the new time period greater, right? Well, if I write it down this way, I have a problem because I know that I need the assumed true difference in there, and I know that I need my difference, but it's kind of hiding here. Because if I think about, well, what if I just move this to the other side? Now what would I have? Well, I would have that the new time period's mean minus the old time period's mean is greater than 0, which is really saying, is that true difference greater than 0? Right? Which would make my null just that true difference is less than or equal to 0, right? Or the complement of that. So it's a little bit trickier to identify the null and alternative because the way in which we usually say, talk about the difference in things is a little bit different, right? But if it helps, you can write it out kind of, I'm saying is, have they increased? Okay, is what I want to test for is that the new mean is greater than the old mean. Well, now I just have to kind of rearrange so that I can write this as the difference between those two time periods. So I've got a less than sign in my alternative hypothesis. So I have, or no, sorry, no, I don't. I have a greater than sign. So I have a greater than or a right-tailed test here, right? We still identify the type of test the exact same. It's based off whatever sign is in our alternative hypothesis here. So we should have kind of C being the right answer here. Now, I said ahead of time, a lot of the times this assumed true difference is 0. And the reason why is because we are interested in, like, have they increased, which really means is the difference greater than 0? Has something decreased? The difference would be less than 0. Have things changed at all? Is the difference anything other than 0, right? And so a lot of the times we're going to be using that assumed true difference of 0 because that's the type of test that we want to run. Okay. So we've got a right-tailed test here, right? The next step is, what would my critical values be? Well, first of all, if I have a right-tailed test, which of these can I rule out right away? Yeah, right-tailed test, my critical values have to be positive. Right? If I'm thinking about what I'm doing when I'm looking up these critical values, I've got known population variances, so I'm using that standard normal distribution. And I'm looking at the right, if a right-tailed test, I'm looking at the right side, and I want to know what critical value would give me alpha in that right tail. Okay? And I think what we're asked for is what the alpha is. So testing at the 0.05 level. So what z value would give us 0.05 in that upper right tail? Okay? Now this is where we have two ways of looking this up. If I just look up 0.05 in that z table, it's going to give me, right, 0.05 is the area in the left tail. So if I look up 0.05, it's going to give me the value I want, but it's going to be coming from the left side of the distribution. It's a symmetric distribution, so if I look up 0.05, I'll get my critical value, but it'll be negative. I could also look up the area to the left of the critical value I want, which would be what? 1 minus 0.05 or 0.9. So I'm going to do it either way. So we'll look both of them up, and I'll kind of show you that, justify that to you. So we look up 0.05. Looks like we're in between these values. So negative 1.64 and negative 1.65. So negative 1.65, but I'm on a right-tailed test, so it should be positive 1.65. Or I could look up that area of 0.95. It's in between these two, 1.6, 4, and 5. Sure enough, I find 1.65 there as well. Right? So my critical value here is going to be 1.65. Or if I want to be a little bit more detailed out to the third decimal, 1.645, which, just a reminder, how I can do that, how can I get it out to the third decimal even if I'm doing this by hand and not using Excel? Well, I wanted 0.05 in the tail. If I remember right, in the student T table, the very last row represents what I would find from a standard normal distribution. So 1.645 here. Okay. So multiple ways of finding those critical values. Any questions up to this point? Oh. Okay, let's make sure. There we go. All right, so what if I want to find the test statistic? Well, first of all, let's just think about what was the sample difference that I found? Well, the sample difference I found, if I look at, just think about this. The sample difference I found was 15.5 minus 9.7, or what, positive 5.8. So I found a positive difference, right? And my assumed true difference, remember, was 0. So if I think about the distribution that I'm looking at, when I'm thinking about the distribution of the difference in my sample means, I've assumed that it's centered around 0. I found a sample difference of 5.8. I'm above the mean, so my test statistic or my z statistic should be positive. I've found something that's going to be a certain number of standard deviations, a certain number of standard deviations above the mean. You know, so I can think about, okay, well, I can turn this into a z-score. Turning this into a z-score is essentially calculating my test statistic. I have a right-tailed test, so the area to the right represents my p-value here. Okay? Oh, I'll blow this up so we can kind of see this a little bit easier. Okay, so how do I calculate that test? I know it's positive, so I think there was one answer I could rule out. Well, we had that equation earlier, right here, right? I have the sample mean from each group, I have my population variance that was given to me for each group, and I have my sample size. So, you know, really calculating these test statistics, I can, you know, draw this out and remember that's going to be positive, but when it comes to actually computing them, you know, it's really just a matter of plugging and chugging, right? Plugging everything in correctly. So I was given those population variances, I've got my 2 sample sizes, 2 sample means, so it's really just a matter of plugging everything into that new test statistical equation that we have. And maybe kind of something that's a little bit different here, that assumed true difference is 0, right? That came from our null alternative hypothesis. Any questions on that? Like I said, I mean, I could write this out again, but it's really just a matter of plugging things into that equation we have. So I find this test statistic of 4.9. We might not be very comfortable or not overly familiar yet, but if I have something that's 4.9 standard deviations away from the mean, what's my p-value going to be close to? So if I go to my standard normal table and I try to look up 4.9, what's going to happen? It only goes up to 3.9, right? So the area to the left of 3.9 is pretty much 1, which means the area to the right would be approximately 0. Well, if I then, you know, if I then look at a test statistic that's even further out than 3.9, right? I've got 4.9. That p-value is just going to get even closer to 0, right? So I basically have a p-value that is, whoops, I didn't mean to do that, sorry. I basically would have a p-value that's approximately 0. So which levels can I reject at? If my p-value is approximately 0, all of them, right? Because my rejection decision is the p-value less than alpha, then I reject. Well, if I have alphas of 0.01, 0.05, and 0.01, pretty much, you know, 0 is going to be less than all of them, right? So I can reject at every single level, right? So we can, I rejected every level here, okay? All right. Any questions on, yeah?
It's small, and it probably doesn't matter, but for when we were finding the test statistic,
Yep.
was it the variance for the second one? It's supposed to be 7.
Oh, it's a 9.7?
Would that still come out the same way?
I think I probably calculated it correct and wrote it down wrong. Someone can, well, you can check real quick. Thank you for checking that.
Just say it's logic there.
Yeah, I say I flipped them, right? So we've got what? 15.5 minus should be, no. What was it now?
That was right.
So 9.7 and 7.8. So this should be 9.7, and then this should be, so I changed the wrong one. This should be 7. So let's double check that it works out to be the same thing. So 9.7 divided by the square root of 25.5 divided by 22 plus 7.8 divided by 32. Yeah, so I did the calculation correctly and it was a little bit around the side. So I'll repost the slide so that number lines up with what we have. All right. Any other questions here? Okay, so you got an idea about how we would work through one of these. Like I said, it's really similar. I mean, the test statistical equation is a little bit different, but the procedure and the steps are the exact same. So we did a little bit in Excel. I'm going to spend a lot more time with 2 population in Excel here, getting us kind of ready for that next Excel assignment. One thing I'll mention, just kind of about how we're going to proceed. So today we looked at examples where we had two sample means and we're looking for the difference in them. I showed you how we can do confidence intervals, a little bit different. Procedure still kind of the same. Hypothesis testing, a little bit different. Procedure is still the same. I'll then show you an example in Excel. Then next class, we'll start looking at the difference between two proportions. Confidence intervals, hypothesis testing, how you do it in Excel. Then we'll do the difference in sample means, and we only have sample variances. Similar to one population, we're going to have to use the student T. So I'll show you confidence intervals, hypothesis testing, and then examples of that in Excel. So I'm kind of breaking up the Excel work across several class periods, so you get a little bit every single day of working through things by hand and doing them in Excel. Okay.
Do you have an idea of when that's going to be due?
That Excel assignment, I'll hold off on posting that until after class on Tuesday. We should be like kind of like today. We should get through the proportion stuff, and then you'll have enough to really get a good chunk of that out of the way. But the due date will be kind of 2 weeks past it, so quite a ways off. Yep. I might make it like a close. It'll be like between a week and a half and 2 weeks. So I'll probably make it due that not that Friday, but the following Friday. So it'll be almost 2 weeks. All right. So the one that I want to start on, we'll start out with this Midwest. Okay. So all I did here, and this should be on the blank file if you open that up. To population hypothesis testing blank. I calculated the sample mean, I used an assumed true population variance here. More often than not, when we're actually doing this by hand, we're not going to have the population variance. But I just said here, someone gave it to me. How that happened, I don't know exactly, but this is where we're starting at. I then found my sample size using the count function just of the undergraduates at this sample of 56 schools in the Midwest, right, Ball State included. I then did the same thing for a sample of Southern schools, right? I found their average enrollment. I then had somehow been given their population variance, and I had the count, right? Just you looked at the sample size here. So remember our sample size here, we can think of this as our N. So one thing you can do, it's kind of helpful if you have data on multiple sheets. So this was my data for Southern schools, but on a different sheet is where I had the Midwestern schools. So I calculated the mean variance and sample size here. I can actually reference, so I'll actually delete this. I can reference across sheets. So, my Midwest data is actually on a different sheet, but I want to put this value on the other sheet. So when I hit select it, notice it kind of references the sheet. Now if I hit enter, so I don't have to type that in, if I just click on the cell, hit enter, sends me back to the other worksheet, and now I've got kind of everything there. Okay. So that's all I did here was kind of copy those values over. So ignore this stuff for a second. We're focused on this today. Let's do a confidence interval for what the true difference in kind of the mean Midwest and Southern kind of university enrollments are. Okay. So I've got the three alpha values, right, that kind of correspond to the 90, 95, and 99% confidence level. If we remember, how would I find this Z value? Well, for a confidence interval, I want alpha total outside of it, which means I want alpha over 2, on either side. So this is where we said, okay, I can use that norm.s.inv. I'm using that Z table, that standard normal distribution, and I'm working in reverse. I know the area in the tail. I want Excel to tell me the Z value I need. So alpha over 2 in the tail. There's going to be one problem with this, if we remember, which is that if I hit enter here, I'm going to get the negative value. Well, I just want the absolute value, so probably the easiest way to do that, use that ABS or that absolute value function. Hit enter, I can copy this down, and I get my 3 critical values pretty quick. It was exactly the same way we did it for one population examples. And as I'll probably grade the second exams first, and then I'm going to start going through those third Excel assignments as well. So I think I'll have the exams done by Tuesday. I'm hoping I can get the Excels done by Tuesday. I'm not 100% sure that'll happen, but I'm pretty confident I'll have the exams done. Yeah, I'm pretty confident I'll get your exams done. I can't make a promise on the Excel assignment, but I'll have it done by next Thursday for sure. So, yeah. This one? Yep. All right, so we use that norm.s.inv because we knew the area in the tail. We're working in reverse here. Instead of telling it a z-score, we're telling it the area that we want in the tail, and Excel to tell us the z-score, or the z-value, I should say, not z-score. Okay? Any other questions on that before we keep moving? Let me see if I can get, have to click out of there. Okay, no, nothing in the chat. Now at this point, we could type this, basically what we want to use is that lower bound equation. I have all the information I need. Oh, where is it? There we go. I could just use Excel to be my calculator here because I have all these values now in Excel. Now, once again, I think it's probably easier to calculate that intermediate step. What's the standard deviation of the difference in my sample means, right? This guy right here. So I'm just going to calculate that as a separate step. So I've started some of the other sections based off what I've seen, the work that got turned in for that third Excel. People that did the intermediate did a lot better. Right? They usually were more likely to get it correct, it was more likely to be correct. So if I take the square root of each group's population variance divided by their sample size, so that was in what, M6 here, and then add in the second group, so here's the population variance divided by their sample size. Okay? So that's all I've done is use Excel to be my calculator because I had the values in there already. I could just kind of click on them there. So now I've got that intermediate value, that standard deviation. To get my lower bound, can you see that again?
You had those two, right?
Yeah. What would you have maybe done wrong? Make sure you're taking the population variance and the sample size of the same population. Like if you flipped these on accident, you would be a little bit, like if I had M5 over N6 and N5 over M6. Oh, did you like this? Or, so try not to use, so here, order of operations actually helps us because it divides them first, then adds them. Yep. So just don't complicate it with extra parentheses. Yeah, basically. So my lower bound is going to be, well, it's built around the sample difference I found. So take the, and actually I think here I said the Midwest minus the South. So Midwest minus the South is how we're going to set this up. So the Midwest will be my group one here. Let me make sure that's how I did it. So test difference. So I have a greater than test. Yep, Midwest minus the South. So I have it typed out correct. So we then subtract to get the lower bound, our Z value multiplied by that intermediate value we calculated, which was the standard deviation of my sample means. So once again, once I had that Z value, I've got everything I need here. It's just using Excel to be my calculator. Okay. Any questions on this? So now, if I want to copy this down so I can build 3 different levels of confidence intervals, what's the issue going to be? Well, the only thing I want to change when I copy this down is the cell reference for where the Z value is at, right? My sample means haven't changed. My standard deviation of my sample means hasn't changed. So I'm just going to go through and freeze all the other cell references that aren't the Z value. Okay. And once again, I don't know why I wasted more time. I could have hit F4 or Control T on a Mac, right, to get those $signs in there. Now, if I wanted to, I'll hit enter here for a second. If I wanted to, if I look at the complete, did I open that up already? No. So if I look at the complete version that's also currently up on Canvas, and once we work through all this, I'll post the blank one after we've worked through it all so we can kind of see what I did in class. Notice here, I actually just typed everything in one line. And it makes it a little bit more, it's just a little bit harder to see if I have a parenthesis in the wrong place or to freeze more cell references. So that's why I like to do it up there in a separate cell and calculate the intermediate value. But you can do it either way. Okay. So let's get out of here. So I've got it in there. I've got it correct now. If I copy down, I should, get my confidence interval now, and all the cell references will be what I want them. This is where we said, okay, go in, copy that, right? Copy that formula, paste it over here for the upper bound, and then the only difference is that I'm adding my margin of error instead of subtracting it. Okay? So just copy and paste. Don't drag it over. If you drag it over, I saw a couple people make that mistake on the third Excel, where when you drag this over, right, what ends up happening? It changes the z-value cell reference to using my lower bound as the z-value. That's not what I wanted. So I'm going to undo that here. I just copy and pasted, changed that to a positive sign, and now I can copy this down. Okay. Any questions on that? Why does this not look right? Oh, it does look right. I'm just, okay. Any other questions on this before we keep moving? Want to see another cell again, or? So it's really similar to what we did for one population examples, just a little bit more, few more moving parts here. Okay. We'll save this. This is kind of some proportion stuff. But I do want to finish out and think about how could we do some hypothesis testing as well. So first of all, we can use Excel to be our calculator, right? We know that the equation that we have for our test statistic is somewhere in this mess of stuff that I've been doing. It's going to be this guy right here. Okay. So I don't think, so let's say I have some different stuff going on up here. We'll worry about this later. Let's just say I want to test for whether or not the true difference is greater than 0, right? So my normal alternative here, let's say I make this, is that true difference greater than 0? I'll assume the opposite is true. I'm going to be dealing with this kind of right-tailed test. Move my mouse, you can see it there. So I'm just going to use that assumed true difference of, is it greater than 0? Okay. Now, I'm doing this for a reason. It might not seem obvious right away, but I put that 0 up here. I wrote that, and actually I don't know why I put it so far out here. Let's move it over so we can see it, probably so it doesn't get confused once the file is complete. So here's my null alternative hypothesis in Excel. And that value I've assumed that the difference is 0. Okay. So I'm going to basically use Excel to be my calculator here. So I want to take the difference in the sample means I found. So go up here, Midwest minus the South. Right. Well, here I'm going to subtract that assumed true difference. Kind of seems stupid because it's 0, but I'm going to do that so that if I want to change it, even though that I wouldn't expect you to have to do that on any homework or exam. I just want to show you, just to give you an idea about after this class, because in your upper level classes, I'm sure some of them might actually mention like t-tests and stuff, which we'll eventually kind of get to see that this basically is a t-test, or this would be a z-test, but we'll eventually get to z-tests. You could do it for values other than 0. So we've got this set here, and I then have to divide by that standard deviation. So once again, I could have entered this all in to this test equation, or I've got that intermediate value already calculated up there, right? That standard deviation of the difference in sample means. Okay. So that should give me my test statistic. Okay. There we go. If I go to that complete file, I think I didn't calculate the intermediate value, so you'll notice I typed it all in. It just makes it a little bit more difficult. All right, so at this point, I've got a right-tailed test. So what I should be thinking about is, I found this test statistic, which I know is a z-statistic because I've got population variances. And I forget the exact value. I think it was 2.61 or something, so 2.6. My p-value would be the area to the, for a right-tailed test, area to the right. Now I have a function in Excel that I can use. I can tell it that z-value of 2.6, and Excel will tell me the area to the left. If I want the area to the right, the only thing I have to do is subtract it from 1. So we'll go to Excel. Okay, I've got a z-value I want to find the area to the right of it. Well, the norm.s.dist function will tell me the area to the left. So I just select that z-score, comma 1. That gives me the area to the left. Now, still to make sure that there's no confusion, because I've seen some of this in the previous assignments, but if I put a 0 in here, it doesn't give me the area to the right. That would be great if it did. I don't know, it'd be great if Excel added that as an option where, I could change this so that if it's a 1, it tells me the area to the left, and 0, it tells me the area to the right. When you put a 0 in there, it's not doing anything that we want to really dive into, because it doesn't relate to what we're doing in this class, and it's not really useful for us. So this should always be comma 1, right? Making it cumulative, looking to the area to the left. Well, remember we wanted the area to the right, so 1 minus that, right? I can put this all in one cell, and now I've got my p-value, okay? Any questions on that?
Can you go back to the stat?
Yep. So I was just taking the difference in my sample means here, subtracting that assumed true difference of 0, and then dividing it by that standard deviation of my sample means, right? Which I had the intermediate. Yes, with parentheses. Okay. Got it? All right. Yep. So, if we look at this, what levels am I going to be rejecting at? It's kind of easy to see on this one. My p-value is 0.004, so is that less than 0.1? Yep, so I can reject. Is it less than 0.05? Sure is, so I can reject. Is it less than 0.01? Sure is, so I can reject. I don't think we're going to get quite enough time today, but if we do, I'll kind of show you how to use these if statements to put those words in there again. But just looking at this, it's very easy to see what our rejection decisions is right now. So what if I want to find my critical value? So if this is a right-tailed test, right? Actually, let's make sure I did that on the completed version. Yep, did a right-tailed test. Okay. So my critical values, right? I'm going to do, all right, I know that when I want to find these critical values, it's similar to what we did before, where was the right-tailed test that we did the example of? I want the critical value that gives me alpha in that right tail. Okay? So in Excel, what that equates to is I know the area in the tail. I want to find the z-value that gives that to me. It's very similar to confidence intervals. I can use that norm.s.inv function. I want alpha total in my tail. Now the problem is the norm.s.inv, when you tell it the area, it's reading it as the area in the left tail. So if I want 0.1 in my right tail, the area in my left tail would actually be 1 minus that. Or, similar to with confidence intervals, I could find the critical value and then just take the absolute. I could plug in alpha, and then I know that's my critical value, is just that should be positive because it's a right-tailed test. But I can do that 1 minus alpha as well. So if I do 1 minus alpha, and then kind of copy this down, I'll get my critical values. Or if I just told that norm.s.inv, if I just tell it alpha, right? Notice I get the exact same values, but negative. But I could have just done that and said, well, I know it's a right-tailed test, so I just have to remember I'm taking the absolute value. And I could get the exact same, right? Either approach is fine. So I've got my critical values. I could, plot them, draw my rejection regions, see if the test statistic is more extreme or larger in absolute value. Or I could kind of use that p-value approach and look, is the p-value less than my alphas? So if I wanted to do that, looks like I have a little more time than I was, for some reason I was looking at the clock wrong. So I think the easiest way to do this is to use the p-value approach. You can use the critical value approach, but for me, I don't know, I just always think it's easier just, is that p-value less than? Now here I don't have alpha entered into a cell. If I did, I would probably use that, but I believe that, actually I do have an alpha, right? I guess I could just use this, right? Is it less than 0.1? So can we reject at the 10% level? Comma, if it is less than alpha, put in the word reject, comma, if it's not, if that is a false statement, put in that we fail to reject, okay? So we looked a little bit at these before, these if statements. When it comes to like the next homework, you don't have to use this if statement. If you want to like just type in and then kind of write the reasoning why. Whereas if you have the if statement, it kind of lets me know you understand the reasoning why. It's built into that if statement formula for whether or not you reject or fail to reject. So I guess I should probably call this the rejection decision. Oh, what's going on here? What did I forget to do? Oh, shoot, my alpha reference, right? So when I copy this down, right, actually, why did I do that? I have my alpha values right over here, right? Here's my alpha values. That p-value I don't want to change. So I'm going to freeze that cell reference, right? Because I want to keep using the same p-value when I test against these different alphas. Now when I drop this down, okay, now I'm rejecting every level, and that's because, oh yeah, it's just updating alpha, but it's keeping the p-value the same. Okay? Any other questions on any of this before we end for today? I know it's a lot, but hopefully, you know, there's a lot of similarities to the old stuff we were doing, so it's not completely new. We'll work through this hypothesis testing stuff over the next kind of like, next week and probably a little bit into the following week, and then we'll kind of go over linear regression, which will be the last thing that we do for this semester, right? So we're getting towards the end here. But really, hypothesis testing, confidence intervals, and then linear regression will be kind of the last topics we cover. Now, before we leave, one thing I just want to show you is I wasn't, why did I subtract that assumed true difference of 0? That's not going to change anything. Well, because for what we're doing, you're always going to have this assumed true difference of 0. But in this example, okay, I can reject the null hypothesis here, which is that, actually, I think we had these are flip-flopped because this is what it actually should be. I was just using that 0 value. We had a right-tailed test, right? So we found, we can reject the null that the true difference was less than 0. But could we reject the null that the true difference is maybe less than 1,000? So not just do Midwest schools have fewer, we're not assuming that Midwest schools just have fewer students than the South. We're assuming that they have 1,000 fewer students, right? So I could play around with this value, and I think here, instead of using that 0 value, I'm now going to use this 1,000, right? That's kind of well, now notice it's not, based off my sample evidence, I don't have as strong evidence that true difference is greater than 1,000 or that it's not less than 1,000. And so, my test statistic falls, my p-value went up, I kind of failed to reject now at the 99% level. And I could really test any of these different, any value here. It's just that more often than not, like I just want to know, the Midwest schools have more students. Right? I usually don't want to phrase things as, do they have 1,000 or more students, right? So it's just, you can do it. It's just not the most common type of problem that we'll run into. Okay. So next class, we'll kind of do some more work in Excel with proportions. We'll do work by hand. I'll show you confidence intervals, hypothesis testing, and that will be on Tuesday. Okay, so make sure you do that online quiz. It's real easy. It's actually just a graded survey. There's no wrong answers. And then also that Learn Smart that I'll kind of get up there, that's due before we meet in class on Tuesday. So you've got today, Friday, Monday, before, I guess if you want to do it over the weekend, should take about 10 minutes. So not very long, just easy points. Okay. All right. We'll see you guys on Tuesday.